Anyway, she is a planetary geologist. Did you get your PhD?
No, my bachelor's in astronomy actually. Before it was an astronomy major, it was called physics. And then my master's in geology there, and then PhD at the University of Arizona. In actual climate.
Better skies in Arizona.
Yeah.
So you see from the future, she is now the science team members of the Dragonfly project that's going to launch in a long time from now. And it's going to go to Saturn's moon Titan. And she's also an authority on Jupiter's moon Io and Mars and Pluto and our own moon. And she's got all kinds of awards, and she's done TED Talks and just all kinds of stuff. So anyway, I can't do justice for how lucky we are to have her here today. So we'll turn it over to Dean Radebaugh.
That's very nice. I really am happy to be here. I've spoken before to this club, but never here. So it's exciting to be able to be on this campus. I think we might have been at UOU one night.
Yeah.
So, and also my topic has changed a little. I know I mentioned I was speaking on the windy planets. You are going to see all of that, but I realized I've got a couple other things that need to go in there too. So this is the big potpourri of around the solar system, sort of leading toward what I'm working on and what I have studied. But also just in general what's exciting, like what's right behind me. I didn't work on this at all, but did you all watch this recently? I just think it's phenomenal that we are able to put these big landers on the surface of Mars. Remember, they're the size of an SUV, they're just gigantic, and they land via this very complicated sky crane maneuver, which when I heard about it the first time, I thought I'd never work. It sounded like little words, just a lot of little words. So that's true to some degree. But yeah, twice now we've gotten it to work, and they lowered these giant rovers onto the surface, and it's physically drilling and collecting core samples to actually be able to bring back to Earth. And so we will have Mars sample return. We can't go to the very areas because they're interesting, and so that's interesting. A little bit of a conundrum that we have is where things are warm and wet. Well, where things are wet, we kind of say, well, that's the place to go look for life, but then will we contaminate it if we go? And so I think the idea is just to make absolutely sure we can clean things very well before we go to those places. So we're going to places where in the past, thanks.
Okay,
Okay, thank you.
And there's a green, this is what I was
Okay, good. And I just was absolutely wowed by the fact that we have video from Mars. And the reason we have that, and this is hard because as we go out to other places in the solar system, everyone will expect video. But we have it at Mars because there are a number of orbiters able to just relay things back immediately. And so we go to other places, especially Titans, I talk about that later, we're not going to have video streaming back, and that's going to be hard, especially if they're going to be decades from now. But to be able to see this kind of detail, this is a picture on the right-hand side, looking down from that, the rocket up on the top, looking down at the rover and it's lowering. And then in the middle is the view of the rover, the surface from the rover is about to land. And then looking back up at the rocket here. So really just amazing. And so here we are in a crater, and this beautiful kind of lobate form that you see right here, lobe-shaped. This is an ancient delta. There's no question in anyone's mind that's what it is. And you're going from high to low, you're bringing material from up in the highlands down into the lowlands and dispersing it as if it were into liquids. And so we assume this crater was filled with water at some point in the past. And so this is really interesting because we're going to these areas that we know were formed by water we're going to landscapes on Mars that we know are formed by water because we know about our studies of Earth. And that's really important because where we've seen water on the Earth, we've seen life. We still don't know about the genesis of life. We don't know if it only happened once and we got lucky. We think probably not. There were so many catastrophes on the Earth that it had to have been able to start up again, we think. And so well, does it just start if it's got the right conditions? And maybe we see evidence of that on Mars. I don't know if anybody thinks we can see modern life there, because Mars is pretty forbidding at this point. But it's important to go and look and see what we have there. Okay, and then also brought a little helicopter. If you watch this, this is just so fun. It has to spin 2,500 RPMs in order to fly there. It's tiny, these giant blades, because the atmosphere of Mars is 1,000 Earths, or several hundreds. And so, so it's just really, really difficult to be able to fly on Mars, and yet they managed to do it. It's lifted itself up and flew a couple of places and turned and took pictures of the rover as it did so. It's a successful technology demonstration. But really, this is the mother lode of helicopters that we've got for the planetary exploration. And this is called Dragonfly. This is the size of a Mini Cooper. And it has 16 different blades. One single blade, I can hold it about like this. One of the blades, okay? And we can fly very easily in Titan's atmosphere. And we'll talk about that just a little bit. It's got a number of instruments on board. This one right here drills inside the leg that will drill in the subsurface and suck some material up into the interior where there's a mass spectrometer. So we'll know what the composition of the materials are on Titan. And we'll talk about why that's so exciting too. But anyway, this is what will happen. It goes direct to Titan. We'll actually launch in 2027, so we'll raise to wait. And then it will just drop out of this aeroshell and start flying. So this is the nail biter, right? So an hour and a half of terror or whatever it is. So, here it goes down across the landscape, taking images as it goes. It's going to overfly the first landing area. Oh, is this okay? Yeah, this looks good. Circle around, come back. It's going to have to do that autonomously because the communication time is 45 minutes to an hour and a half with Saturn. And it's Saturn systems, right? Then it will be able to just stay landed for a number of days, weeks, and then can pick itself up and fly to the next spot. It should operate for a few years. So we'll be able to learn a lot, cover a lot of ground. This is that intermediate between orbiters and these rovers on the surface. The rovers have done great, tens of kilometers. This will be hundreds of kilometers easily.
Do we know what visibility is in the atmosphere?
So we know from the Huygens probe that landed on the surface that it's not as good as we expected. But once we came down low enough, we could see tens of kilometers off into the distance. So that's good enough for us to be able to operate and get into the landscape.
What will power?
It's got a radioactively charged battery, so radioisotope from the yeah, so far the mock-up I've seen is about this big, and they're still working on the details of exactly what they're used.
What do we know about the terrain of Titan? I mean, as far as variation in the mountain peaks and valleys?
Right, yeah, we've got to be concerned about that for navigating, right? It seems like the topography overall is pretty subdued, and so the distance from the base level up to the highest peak is 3 kilometers, so that's pretty rare. Most of the time it's just hundreds of meters. Just stand back a little so just closer to the mic. Okay, oh yeah, sorry. And so, thank you. You're welcome. So I think that in general we're pretty safe, and then also there'll be a number of systems that will help in terms of navigating, so it won't run into anything and put itself. Yeah.
So, what's the gravity ratio on Titan compared to Earth?
It's similar to Earth's moon.
Okay.
1/6.
The atmospheric pressure is.
The pressure is the same as Earth's at the surface, which is really remarkable. Titan has the same air pressure at the surface as Earth. What's that?
15 psi.
Sorry, I don't know if I
15
know.
pounds per.
Right, I know, and I can't remember if that's true or not. Yeah, okay. But then also, the density of the atmosphere is 4 times greater at Titan's surface. That makes it easier to fly. That's very cold. It's 90 degrees above absolute zero. And because it's so cold, it's dense, it's a pretty benign atmosphere. It's perfect for flying.
And what's the mass or equivalent weight of the
Do you know, I don't know if I know that either yet. I forget.
Stop asking.
It's their show.
How far do you think it'll travel in its total?
I honestly think it'll be hundreds of kilometers. We can go as much as, tens of kilometers in one hop. And then spend a few weeks there, and then tens of kilometers more to another hop. And I think it'll start to be tempting to be like, oh, here we are. We're landing in a region called the Selk region, Selk crater. It's an impact crater. And we're interested in what the impact crater excavated from beneath, because it might have liquid water as it excavated that, and we have liquid water interacting with surface materials which we think are organics. I'll show you some pictures of that, hopefully. And it's just by nature of where it is in the solar system. There's lots of organics everywhere in the atmosphere. There's methane in the atmosphere. It rains onto the surface. There are pools of methane. And then heavier organics that we saw with the Cassini mission. And if those things can interact with liquid water, then, this is a great place to, it's called a prebiotic chemistry. Just kind of like what kind of chemistry is happening. We can't say we're going to find evidence of life because, you'd fail at your mission, right? Most likely. But we will look and just see, of course. We'll have a lot of things that we can do, a lot of tests we can do. Okay, here's a picture of Titan, and, oh yeah, go ahead.
I was just going to say, what was it about Titan specifically that made you guys choose that for Dragonfly? Is it just because of the ideal flying conditions?
Yeah, it's a number of things. The first is that we saw this even with Voyager and said, wow, what is going on? It's a thick atmosphere, nitrogen rich, just like Earth's, but then all of these organics in the atmosphere, hydrocarbons. And so actually they built the Cassini mission on the back of that knowledge. Like, what is this place? It's got all these hydrocarbons and methane rainfall on the solid surface. Let's go and look and see what's going on. And there's enough organics that creates a haze in the atmosphere that makes it difficult to see to the surface. But we did still send a probe down. This is a Huygens probe. It could have splashed down in lakes of methane, but instead it landed on a solid surface. And it saw river channels. These are better developed river channels than anything we've seen on Mars. So they might even be happening now. We've seen some evidence of rainfall on Titan with the Cassini mission. And then you have this riverbed with all these rounded cobbles. The lander actually vaporized some methane off the surface, and so it's like humid with methane everywhere, and so just an interesting place. It looks very Earth-like, doesn't it? It's like the backyard in Tucson, really. And then after a while we found, there are actually big rivers and seas of methane up at the North Polar regions. We won't be able to get up to these lakes or seas because the spacecraft has to communicate direct to Earth, so we need to stay in the equatorial regions. If we get too far north, we'll not be able to see Earth and communicate. But I have some pretty strong hopes that we'll find some liquids standing on the surface, even though we're kind of in the desert region of Titan. We'll talk about that in just a minute. I still think that we could maybe observe some rainfall and some swamps and things like that. Well, we've painted some pictures of what we think Titan looks like. So this is from near-infrared mapping spectrometer. Actually, it's visual and infrared mapping spectrometer, VIMS, and it's sort of like assigning a color to each composition that we see on the surface. We only broadly know the compositions because, as you might know with organics, you can just sort of have any peaks and troughs that you want in terms of atomic mass. There's just lots and lots of possibilities. You just add another carbon hydrogen to the end of the chain and you can get what you would like. And so all we know is, okay, there's lots of organics and some water ice maybe. And so we have, but look at how interesting there are these big kind of continental regions. We think this is just a big mountainous area with some river channels. And then there's the kind of whitish regions that are just empty plains. And then we have all of these big brown areas all across the surface. Where those brown colors are, it's filled with sand dunes. Something like 20% of Titan is covered in sand dunes. That was totally unexpected, and it's a major landform. We think these dunes are a lot like the big dunes of Earth's big deserts, like Arabia and the Sahara. This kind of dune is really abundant in those regions. I didn't even know about them before. They're about half a mile wide, hundreds of miles long. They're spaced from each other a mile or two. It's really crazy. It takes you a whole day to go up and over one with your instruments. Maybe you can cross the floor and get to another one barely within your day. They're just very big. And what's pretty neat is that Titan's dunes are exactly the same size and shape as Earth's big dunes. What does this similarity of size and shape, I think it must be related to the same atmosphere. The atmospheric pressure being the same at the surface. Makes some sense to me. Okay? Okay, so we're going to these places. We're going to different areas on the Earth to understand what's happening on Titan. And so this here is in Namibia, the Namib Sand Sea. You can kind of see, oh yeah, it took us a while to get this little radar instrument all the way up the hill. I try to make the students do as much as I can, but sometimes I need to do a little work too. These are mega dunes, and they're big, and they take a long time to change and to move. What will we find at Titan? Because this mission is focused on the dune regions. That's what's at the equator. Will we find that they're active, that they're moving around? Will we find ripples on the dunes? And then also the crazy thing is the dunes on Titan are made of organics. Okay, what does that even mean? I try to picture it. I try to make up a material. Grape nuts? Grape nuts. The same color, the same composition, the same density. Grape nuts. I think that's what they're made of. Yeah.
I'm trying to visualize in my mind when you told me how cold it is there, that there is a gaseous atmosphere, and it isn't by pressure or temperature reduced to a liquid.
Yeah, that's right. It's just at the right temperature. It's 90 degrees above absolute zero, so that methane has to be a liquid. So it's basically liquid natural gas, right? But nitrogen can still be a gas. But if we go out to Triton or Pluto, all of a sudden that nitrogen, that's 30 or 40 above absolute zero, that nitrogen is collapsed onto the surface of the glacier, right? Or an ice cap. So this is just ahead of that. And isn't it fun that we have bodies at all those different temperature
Just
regions?
that sweet spot.
Yeah, exactly. Yeah, and so you had to wait until you're getting all the way out there to be able to have a body that could have Earth-like processes and landscapes, but with all these different materials. And so that's how.
Yeah, I've heard that the methane operates like water here, when the water operates like rocks.
That's right. It's bedrock, and it's basically like the granite basement, or the schists at the bottom of everything on the Earth. That's water ice. It's just very, very solid. And so, yeah, you just kind of shift materials to their different roles as you go farther out in the solar system.
Ignorant question, are there any life forms that can survive in methane?
There's some fun speculations about that. Chris McKay is an astrobiologist, and he's done a number of papers that have ideas about this, and he says you can use methane as the solvent for life, similar to what water does. Water and carbon-based life are just so good at what they do that it is hard to replace them. So water, being a polar molecule, is able to help exchange materials back and forth across cell walls, and methane doesn't do that as well. But then, for reasons I don't know if I understand it as well, you can grow a cell to be much larger. So you might have like a meter-wide cell if it's operating in a methane environment. And so you know, it was a TV program, you could kind of see these like cells floating on the seas, and picture what's going on. So yeah, and Dragonfly will carefully look for evidence from both kinds of life.
That's the carbon in that.
I don't know. Carbon might still be able to do that because you can still have solids, a whole range of whatever with carbon-based molecules.
Okay, I have a two-part question. Does Titan have any volcanic activity?
We think so. And so what would the volcanoes be?
Heat, water.
Yeah, it would be from heat, but it would melt ice. Yeah, it would melt water. These are called cryovolcanoes. And it would melt water, but here's the trouble with cryovolcanism. What happens when you melt ice? What is the water like compared to the ice in density? It's heavier. And so when you melt this ice, it just sinks down to a global ocean. It's below the icy crust. And that's different from silicates, where if you melt rockets, it becomes buoyant, it's less dense, and it needs to rise up and erupt. So we actually see very little just in-your-face evidence of cryovolcanism in the solar system for that reason. It's just hard to do. But we think there are a couple of, there's one mountain that's got a big pit in the middle and then a lobate flow around the outside. And it's really hard for it to be something besides a volcano. So maybe there are a couple of isolated examples. And that's another good place to go and look for evidence of liquid water interacting with organics and see what happened there.
Okay, so part two.
Yeah.
So I teach about extremophiles at BYU. So it sounds like Titan could be a target for either thermophiles, methanogens, or cyclophiles of some sort.
What was the last one?
Cyclophiles?
What is that?
Or, okay,
Is
so,
that dry?
cold-loving,
Cold,
like archaea that live on glaciers,
Yep.
for example.
Exactly. I mean, all those things, absolutely, we should be prepared to look for and see. And isn't it interesting, the more corners of Earth we look at, the more we see that there's biology. And so yeah, I think it's not impossible, and we have to look. Let's see what happens. Okay, well, what I'm really excited about is that we get pictures at every scale. I'm a landscape geologist. I want to understand what happened, how things formed. And so I get to see the sand dunes at every possible scale. And I've just been so jealous of Mars forever because, I mean, they get everything they want. Here's some sand dunes on Mars. They're so beautiful. And then one day in a meeting, I saw this picture, and it's sand, a handful of sand on Mars. I was like, oh, you gotta be kidding me. They get everything, which is great. I'm glad they're doing that. But so we'll be able to have that. We'll have a microscopic imager that can look at the sand, and that's really cool. About sand, sand can tell you a lot about the region all around, because there are a lot of processes that have to happen to first break down material and then sort all of the sand and winnow it and move it to one place or another. And so the dunes I was showing you before, the sand in that crater, in Gale Crater on Mars, we could find little flecks of, oh, hey, there are evaporites. There must be evaporites in this crater somewhere. Oh, there are a bunch of basalt materials, so that's from explosive volcanism. So you can kind of piece together a broad history. And I like this analogy that I've been to a couple of glass sand beaches, and they're so beautiful. You pick it up, it's glass. And when you really think about it, I was like, wait a minute, I kind of walked around the corner, this is in Hawaii, and there's a big trash dump there with a bunch of glass bottles, right? And so you can predict, you're looking at the sand like, oh, I'm sure what's happening around the corner. And so that's really the value of a handful of sand. You don't have to go to every little spot. It's all kind of collected for you in one place. Okay, and then also we're going to use that mass spectrometer up in the belly to be able to sort out the molecular weight of these molecules that it can bring up inside. And you know, if we see peaks at certain molecules, that will tell us if something's sorting these things, if something preferentially using those particular molecules or making those molecules, and we'll even be able to look for something like chirality. Do you know what this is? It's a handedness to molecules. And we on Earth have almost universally left-handed chirality. It should just be 50-50 if it's naturally occurring. And so if you find, oh, if this is all right-handed, then maybe something's preferentially using that different kind of spin to its amino acids and other things. Okay, so stay tuned. I'll come back and talk more about it as we get farther along. And I've got a couple more things on Dragonfly at the very end. So as I was starting to think about all the dunes on Titan, I sprung off into the deserts of the world and found that they're very interesting landscapes, and there's a lot going on, and it's controlled by the wind. We're not used to that. I think many of us probably thought that delicate arch and other things were created by wind, carving out the sandstone, but no, it's from water. From water, the water is just relentless. It flows across things. It erases any evidence of wind fairly quickly. But there are some places on Earth where there's not water falling. It's a hyper-arid desert. Like this right here, this is the Puna or Altiplano of Argentina. And here the wind is in control. And you can see a couple of broad, gentle ripples. These are gravel ripples. And then in the distance, there are some towers. There used to be one uniform layer that was white, and it's been carved by wind into towers. And these are really beautiful. They're called yardangs. I did not take this picture. I wish it is. It's in China, and it's a field of yardangs. Look how straight they are, especially compared to sand dunes. Sand dunes kind of meander just a little bit, but these are dead straight. And the wind, as far as we know, mostly blows down the yardang. They even have sort of like ballistic forms to them, don't they? Or sort of like submarines. It just looks like they're plowing through the wind or through the substrate, but it's the wind that's blowing down the axes of these features. So we've spent a fair amount of time in the Puna of Argentina studying these landforms, trying to understand them better. They have a sort of teardrop shape, and then you can also see these beautiful, striations. These beautiful striations from the wind blowing down the sides of the Yardang, and the wind is carrying sand, and the sand is shaving away the material from the rock. This rock is volcanic ash, and it's pretty soft. It's hard enough that I could walk up on the sides of this easily, but you could take a chisel and easily carve it out, and so it's eroded by the wind over time pretty easily. And these gravels are everywhere. We're not quite sure how the gravels, oh, I'm sorry, it's not quite, I can even hold it. That'd be better. The gravels are kind of everywhere. Okay. And there's got to be a role that the gravels are playing in the formation of Yardangs, because everywhere in the world we've got gravel ripples. And do gravels get picked up by wind and they erode? We don't think so. That's a lot to ask. But still, it makes for beautiful landscapes. Look at this just gorgeous terrain. And we spend a lot of time just playing. I love being in them. You can explore and wander down these canyons of Yardangs. One year I lost a glove. It just fell out of my pocket. And then the next year we were just wandering down through these, through a 10-kilometer tract of Yardangs, and all of a sudden I looked down and there was my glove. And it was about this small, had been shrunken by the wind and the sun. And oh, God, I love that. I always bring students with me, and they add a real energy, and just they see things that I don't when I bring them out in the field. I love that. This is Jonathan, and he's measuring these things protruding out the end called Dados. What's a Dados in Spanish? Fingers. So that's exactly what's going on. There are little fingers protruding out in the wind. That's a rock contained in the ash. It's harder than the rest of the ash, and so it kind of protects that little tiny pillar from the wind, and everything else is eroded away. So that's a really good indicator of wind directions all across the Puna. And so that's what we're doing. We're kind of modeling the wind directions, and here's a really rough first scale model around one of our test Yardangs right here, trying to understand what's going on. And we find, based on the Dados and other things, that the winds recirculate on the back. And I always wondered that, why is the wind blowing this way on the, it should be going from the right to the left, but it's going from the left to the right here. And so there are a lot of complex things that are happening in terms of the wind patterns. And why are we doing all of this? A lot of it is because we have lots and lots of Yardangs on Mars. They're all oriented lots of different directions. And we have one or two weather stations on Mars, and we don't have them here. So we could sort of use them as proxies for wind across the surface of Mars, which is really useful.
Looking at this wind pattern, it's very similar to water patterns.
Sorry, my fault.
Kayaking and rafting, and you're looking for the same type of patterns when you're traveling on liquids.
Yeah, that's true. That's true. And really, that's exactly what's going on. Is it's the same thing as it's operating in a fluid, just like it would operate in water, but instead that fluid is air. So I agree. I've seen a lot of things that look like submarines and look like other things, and that's pretty cool.
I might have to just stop for a second.
That's
Sorry.
Okay, no problem.
Take a quick break.
If you have any other questions while we're thinking about it, yeah.
So are we suspecting these Yardangs on Titan?
Yes, there even are some on Titan as well. And there are a lot of things we got used to looking at dunes and what dunes look like. All the images we have on the surface are radar images, which are kind of different from visible. They kind of tell you about the texture of the material. And so one day we were all looking, and there were some sort of dome-looking shaped things and some very straight-looking, regularly spaced features. And I kind of was puzzling everybody, oh, maybe they're from extension or they're cracks or something like that. And then somebody else said, I think they look like Yardangs. And I remembered seeing Yardangs, just like, oh, that's got to be what they are. So we did some measurements, and it makes sense that that's what we're seeing.
So what about the wind on Titan? Do we know its intensity?
There's some model predictions that during storms it can reach 15 meters per second. And that's plenty to be able to do a lot of work. Most of the time it's about a meter per second if we need it to move sand around.
So is the craft able to withstand all of that?
Yeah, it can. I think if it's a storm wind like that, hopefully we'd be able to see that coming and not be up in the air. A meter per second, no problem. It's amazing. They're doing because it's a quadcopter. Well, for one thing, like, does anybody have a drone that they work with? I mean, mine should have died long ago the way I fly it, but it protects itself and it doesn't let me do dumb things to it. And so it's pretty great. And the mock-ups they have, Penn State University is actually building some of the mock-ups, and it's really stable. It picks itself up and it just moves around, and you can blow a lot of wind at it and it's okay. So it seems like it'll be all right. Yeah.
I was wondering if anyone's done wind tunnel studies, making models of some of these features and looking for the interactions, because it's all vortexes and things created off of shapes.
Yes, early on there were some wind tunnel studies. There's a planetary scientist called Ron Greeley. He also kind of spearheaded the Europa mission. That he passed away a little bit early, but that Europa mission is happening, which is really great. And he had gone out and studied Yardangs and did some wind tunnel experiments, but we need more. So I hope people would go and do those there. Right now we're just doing some computer models. So let's see. This is
I think I disabled your thing.
Oh, that's okay. Oh, good. This is our test Yardang that we found in Argentina. And we planted a whole bunch of anemometers, wind meters, all around the outside of it. And then we also...
What altitude are you at?
10,000 feet. Oh, what's that?
That's what the remote people have been hearing the whole time.
What, oh, just the... They've been hearing the sound of this thing? Oh. And I don't know how to forward once I do this kind of craziness.
That thing isn't working anymore because I unplugged it to make
Oh,
the thing
okay.
work. That's why.
That's all right.
So,
Are they hearing now okay, or do
they're
we
hearing now
have to-
okay, but you lost your mouse. It must have been
Oh, that's all
interference
right.
with the mouse.
Okay, so then we set off some smoke bombs. Really windy there a lot of the time. But the smoke bombs can show that nice movement over the back. This is from a wind that's not from the front of the building. And so we see the whole sideways when we're there. So we can have backward winds. There's Laura up on the top. She's in charge. That's cool. I know, yeah. So what did we find? Well, here are wind roses that kind of show the direction that the wind is coming from and blowing to. So we're kind of looking at, just took ourselves up and over and looking down on top of it. And then you can see that there's that backward wind kind of from the side of it. We think that's what's making them isolated. They should just be long lines like the ones in China, but they're broken apart here. And I think it's because there's an important backward wind that's coming up and around. And so we're just kind of getting a handle on that. And yeah, taking breaks while we test all the anemometers as we go forward. Okay, does the wind ever get strong enough to get up to the top of the Yardang? Yeah, we've been in a couple of windstorms. Sorry, I'm gonna just go just a hair lower here. For yourselves. Yeah. There we are. Like, oh yeah, it does erode all the way up to that layer. It's good to, we're always happy when things like that. And then there are some other landscapes that are really unusual, and we managed to get our drones up and fly across these landscapes, and they're just like waves on the ocean, aren't they? So beautiful. Are these pre-Yardangs? Are they after the Yardangs? What are they? They're just these bedrock ridges, and there's a kind of arms race to be the first ones to figure out the bedrock ridges. So who knows what will happen. Oops, what did I do? Okay, I want to just go out, if I got time, to just a couple of beautiful images as we go forward for the astronomers. How do we know this is taken from a spacecraft? Sun's behind it. This is a beautiful image from Cassini. Isn't that gorgeous? And little did we know, there's that beautiful diffuse E-ring way out there on the edges. What is making it so diffuse? Well, a little Enceladus is contained in there, but it turns out, oh yeah, and if you look right up in this corner, right there, there's a tiny little dot. Guess what that is? Earth and the moon right next to each other. Isn't that great? Fun for us to be able to look back and see just how far away we are. So what is that diffuse E-ring from? Now we know that there are geysers or jets, volcanoes of water gushing out of the interior of Enceladus. This is small, it's only the size of the UK. Why is it hot inside? There's a little bit of tidal energy, maybe radioactive decay, and at the very least there's water coming out from the interior where it's been in contact with rock. So this is a very exciting place in terms of astrobiology. We're trying to figure out how to fly through that plume without breaking everything up into shreds, because you go 17 kilometers a second, and we got to figure out how to slow down. My artist friends like to take my pictures of Antarctica and then put me on a different planet. So that's pretty good.
Well, then you would say I've been there.
Oh yeah, that's true. It's the wrong orientation. Yeah, no, I can say I've been there. That's what I like. And then, of course, this one. Does anybody know the name of this one? It's Mimas, and that's no moon. That's star. Exactly. This crater Herschel was not quite big enough to break apart Mimas. Its surface is covered in craters, so it's very old. And we use cratering to help us determine age of surfaces all across the solar system. I just love the gorgeous images that came back from Cassini of the rings of Saturn. I mean, how many patterns can you see here? How many wavelengths across this? And these last orbits where we went between the rings of Saturn, we were able to look carefully at the rings and see some gorgeous detail. And this is a result of the spin of the rings plus the tug of gravity on the rings by Saturn. It creates these beautiful patterns that get propagated out. But remember, the rings are blade thin. They're just a couple hundred meters high and 100,000 kilometers across.
Astronomically speaking, time frame, those rings are very temporary.
That's right. The latest thinking is that they're just maybe a couple hundred million years old. That's the age of the dinosaurs. That's the last 20 minutes on the 24-hour clock of the solar system. So we got lucky to be able to see this. What is that based on? Brightness of the rings. These are really bright compared to some other rings we've seen. Seems like something just made them, right? And also we know there's a rain of that ring material onto Saturn. And so if you kind of look at how fast we're losing material, that's another way we can kind of get at that estimate. That's only emerged in the last about 5 or 6 years that we think they're fairly young.
And besides Enceladus, is there any other sources that they've identified?
No, we think probably what happened is that there was just another moon, and it probably wasn't even the size of Enceladus. It doesn't have to be to make that size of rings. It just needs to be 100 kilometers across. So it may have strayed into the Roche lobe and just got torn apart. There might have been other interactions between the satellites to do that.
Do the rings, are they in the Roche lobe of Saturn?
Yeah, they are.
Okay. So there's no way that anything could form or
That's right.
come together.
Yeah, they're little tiny moons, the shepherd moons, and they range up to 100 kilometers across. Is that right? I actually don't know if any of them, I feel like Pandora is that big, but I know Pan is only 30. But I'd be surprised if it was 100 kilometers across. Should go look at that. Okay. Let's go back inward just a little bit. I'm meandering around to show you some really amazing videos. Have you seen these images from the Juno spacecraft? This is not a painting. This is an image of the surface. To me, these look like the most amazing paintings I've ever seen. The camera was an afterthought on the Juno mission. They thought, no, we don't need it. It's not a camera mission. And everyone said, well, I always need to do outreach. Let's just put one on. And so they put one on at the last minute, and it's been just amazing to be able to see, especially the polar regions where things are a little bluer near the equator. We're breaking apart organics and making the kind of more orange colors, but the bluer hues are up at the poles where it's cold.
These aren't false color images then?
They're probably a hair false, but they're pretty close to true.
Interesting.
Yeah.
Non-Hubble palette.
Yeah. Well, I don't know. They might be doing a little bit of license. And then here's the great red spot. Look at all the detail of the storms around that. Remember, it's an Earth-sized storm on Jupiter. And this is because of the deep atmosphere. There's nothing to stop it once it moves. And then also Jupiter rotates every 11 hours. It's that upper atmosphere. Every 11 hours it's spinning around. And so there are bands and zones going in opposite directions of each other and making these big storms. And then can you see this tiny object right here hovering off to the left? Anybody know what that is? That's Io, Jupiter's moon Io. Beautiful Io.
Was that a shadow?
Yeah, that was a shadow from Io on the cast on side. It's pretty neat. This is a little bit false. The blues would not be so blue. Everything would look more yellow. But this is the size of Earth's moon, and it's got a much higher albedo. Imagine this in the night sky. Big yellow moon up in the night sky. It's spectacular. Every dark spot you see here is an active, recently active volcano, recently erupting even, because it has to be warm or else sulfur dioxide frost condenses on the surface on top of them. And lots of sulfur is coming out of the interior and landing on the surface. It's the volcanic moon. And this is because of the tidal interactions with Jupiter. So for every one time Ganymede goes around, Europa goes around twice, and Io goes around 4 times. And that resonance keeps the orbits eccentric. So sometimes Io is close to Jupiter, sometimes farther away. It's like squeezing a ball every 40 hours. You squeeze it by 100 meters. And that's the friction that happens inside. And we can even see that from Earth. So this is Keck adaptive optics images of Io. Isn't that spectacular? From Mauna Kea. Not the lower right, that's overprinted on some Galileo data that we have. But this image in the upper left and below that, we have that data from Earth. And so we can monitor now that, well, Juno's able to look too, but for a while it's just telescopes that can look at Io. And there are big lakes of lava filling giant pits. This pit is 80 kilometers across. And so in an effort to better understand these things, recognize this guy up in front, this is Bryce, I go visit volcanoes around the Earth. And part of the reason is, well, what does the temperature of a volcano tell you about what's happening on the surface? And temperature relates to composition. And also, if it's a really confined hotspot versus a spread out hotspot, what is the eruption like? And so we're trying to get some close-up data to help us understand that. So we went to Iceland this summer. We've been hearing about this volcano erupting. Seems like it was coming from a deep source. It should last. It's hard to do a whole flight in case it shuts off 11 hours before you get there, which has happened to me before. So not here, but somewhere else. So we went and Bryce was like, I'm so excited to see lava. I said, I hope you see lava. And then we saw it. Oh, here it is. Look, we could just turn around and go home. And then out of the corner of our eye, like, wait a minute, what is going on over here? And then this is not slow motion. It's just very, very big. So hundreds of kilometers high, hundreds of meters high. And the fountains are about a half a kilometer away from us, but we still feel the heat, right? We do this every 15 minutes. And it's a big river of lava. We think that river's like 8 or 9 people laid across end to end. It's really hard to tell scale. But like the eruption of, I just sat there in awe for days. How do I get to the next one? There we go. And it was really, really hot. It came out of there so hot it would come zooming by and just consume its own crust. I've never seen anything like that. And that was a surface flow close by. Oh, here's another neat one. This started to behave a little more like lavas we've seen at Kilauea, Hoi Hoi, and other things, but you'll see it consume its crust again in just a minute. It came from very deep inside the Earth, part of the mantle plume that's underneath Iceland, and is steadily feeding these volcanoes. We're in gas mask the whole time, trying to talk to each other. There it is, consuming its crust. You can actually get up to this lava if it's, and we got so lucky it did come right next to, the cold ground, so you could scoop it out. And we kind of hammered out some coins and other things like that, which is really fun. But you have to do it quickly. Big open channel came right down next to me, and I'm doing this for the temperature. It's really hot. Even that far away, really hot. It's hard to take. Others. This is maybe the video of my life.
Are the fumes coming off of that molten rock toxic?
Yeah. It's hydrogen sulfide, sulfuric acid. So you cough if you breathe it in, and you can do that for a few days. It's okay, but if you wear the gas mask, it's a lot better. And because we had that, we could get close. Look at the bubbles coming up through that. Isn't that just so beautiful? We got to see it at night, which lasted about a half an hour, because it's late May in Iceland. But notice too, there's even a crust forming on the stuff as it's flowing rapidly out. So that always teaches me, well, crust will form quickly because the atmosphere is ready to cool it. And how does that affect what we see? And we did get a drone up. We had to run around 45 minutes to collect it because it had to emergency land on the other side of the lava flow field. But meanwhile, I got some cool video of these big expanding ponds, which are just lovely. And what I can do is use a handheld camcorder to take a picture. And this camcorder has been calibrated against a hot rock cooling in an oven. So we can set a pixel value for a temperature. And we have a temperature of that remote observation. So that's 1050 Celsius. And that's really similar to what we observed, what people observed from taking a thermocouple and measuring the lavas near the surface. So these are really valuable. We've done this at a number of lava lakes and other things. And you can see that, yeah, the edges even of those fountains that are ejecting up, the rinds cool off quickly below that eruption temperature. And that helps us understand what we might be seeing on Io, where you've just got a couple pixels over one volcano. But what we'd really love to do is get up close and personal and have a dedicated mission to Io. So here's the idea, Io Volcano Observer, because we don't really understand how such a hot planet can cool off. You know, how is it losing its heat? Is there a magma ocean? Here are a couple of ideas for what the interior might be like. Is there a full ocean of magma? We think that based on the magnetic field data, there's something conducting under there, and so there could be a magma ocean, or it could just be a magma sponge. That's another word. Or, you know, and what is going on? Could we look carefully at these eruptions? And it should be a lot like early Earth, because early Earth was very hot, and we have volcanic eruptions like that.
Iron core, molten iron, possibly.
Yeah, we think probably, but there's no self-generated magnetic field.
That would be my next question.
Yeah. But you know, we've just discovered Mars's core is liquid. Isn't that fascinating? The InSight mission landed on the surface, finally accumulated enough data to return a model for the core, and it's liquid. But there's no magnetic field. Why not? Because the whole thing is liquid. There's not a solid inner core, and the cooling of that inner core delivers heat to the outer core that causes convection. So if that is not happening and it's just all liquid, it doesn't have to do anything, it just sits there. We think that's the reason. A similar reason might be there for Venus, why Venus doesn't have a magnetic field. So that was really fun. It's actually liquid. Now I'm starting to think the same could be true for Io. There's so much internal heat. So this made it down, but there were 4 finalists for the Discovery program. It was announced this summer, and we figured they'd pick 2. So there were 2 Venus missions up. One is a Venus lander, one is a Venus orbiter, another is a mission to Triton, a moon of Neptune, and that was pretty new, kind of immature, it's hard to expect much. This mission has been run up a couple of times, it was in great shape, so I was like, oh, they'll pick a Venus and they'll pick an Io, and they picked 2 Venus. 2 Venus. So it was Venus's time. It's been a long time since we've been to Venus, but phosphine made a big difference, that's right, yeah. This discovery of phosphine in the atmosphere means there's the possibility for life in Venus. Like, who would have thought it could be on Venus? But at the very least, it's an interesting exoplanet analog. It's an Earth that wasn't, right? And so it's important to go to Venus. But it's amazing how resilient people are. The PI is like, well, let's just put it up again, you know, for the 4th time. That's a lot of work. Okay. I know I'm getting up next to time. So I've been to Antarctica a few times, and I really think this is a windy continent. It's always windy here. This whole terrain started out flat, and then tints that cause wind tunnels around the outside, and deposition of these big features. This is going to be another loud one. The winds really get ripping here. They make dunes and ripples. I'm always delighted to see the dunes and ripples everywhere, and yardangs. That's only their sastrugi. And we go there to recover meteorites. We can find places in Antarctica where hundreds are able to be collected every season, which is pretty amazing. So these are free samples from space. It only costs us $1 million every season. And so that's like nothing, right? You can collect these pieces from outer space. And most of them come from the asteroid belt. They're those little chunks of failed planets. This was the biggest one we found, size of a head. Most of them are kind of small. This one is special. It's black and shiny. We put on the mark, because we can't do the lab studies in the field. We put in the notebook, hey, look at this one first. And it turns out this is from the moon. And so we actually can get chunks from the moon sitting on the surface in Antarctica. I should mention that this thing right here is an Apollo era counter, a field counter, and they brought those with them to Antarctica, but these are just spares they have back. And so they send them out with the Antarctic program because there's a tie to Johnson Space Center, and that's where we return the samples to. Okay, so free samples from the moon, that's really amazing. And Mars and Vesta and other bodies. We don't know where they came from, so there's still value in Mars sample return, things like that.
These meteorites have been there for a long time or newly placed?
It's a whole range, as long ago as 3 million years, because they can be preserved on the ice sheet for a long time. They could even be today, that'd be really lucky. But we go to these kind of strand lines where the glacier has carried everything to the base of the mountains, and then the ice sort of sublimates away and it leaves behind whatever it was carrying. And so they're extra big numbers. I always try to say it's like about one every skyscraper. That's this kind of volume. That's why we want to be on snowmobiles, and we can collect 50 in a day if it's a good day. If it's windy like that last one, we stay inside and eat pieces of chocolate with butter on it, And then sometimes we search in a moraine, and just by color and by shape you can tell the difference. And humans are much better at it, anybody, than a robot still. And so we still send people out. It's hard to keep us alive, but it's good. And a lot of times NASA will send astronauts out with us because it's a good intermediate training ground for them. They learn how to work in close quarters with people, stay in the field for 6 weeks, live in a tent, and go out and collect things. And so they really enjoy when they can get to come along. And here's our haul for one season, along with the juice boxes. Those are amazing out there in the field. Okay, one last place to go to. I'm sorry this is so scattered, but we're almost done, and then we can do some questions too. Okay, Pluto has been just amazing. I mean, think of what we could see. It was like 10 pixels across until 2015, and now we've got detailed pictures of the surface. Now we're at that region, 30 degrees above absolute zero, where all of that nitrogen is sitting on the surface in a big, thick glacier. And occasionally some of it will get liberated up and form part of the atmosphere. Some carbon dioxide will, but there's methane ice, there's carbon monoxide ice, there's nitrogen ice everywhere. And the landscapes, once again, they look just like Earth, don't they? Look at the rugged mountains made of really rigid water ice, and then a gently flowing glacier out across the plains made of toothpaste-like nitrogen. And so you have something filling every niche on this body. And we're so fascinated by that idea. We're starting to realize that's true across the solar system. And yeah, a friend and I were looking at this on Facebook one day. Hey, aren't those cool dunes on the surface? And then he's like, seriously, what about the dunes? And it's like, I don't know. So I wrote the guy leading the mission, hey, who's working on the dunes? He's like, nobody, there's no dunes. Oh, we've got some dunes. And so we kind of pitched our idea, well, they look like dunes. That's sort of a strange argument, isn't it? Doesn't go over well with the physicists a lot. They look like dunes. I know they do because I've seen them in Death Valley, and they look just like those dunes. They kind of get coarser near the middle, they pile up near the middle, they're bigger, and then they get smaller away from there. They're regularly spaced, they meander a little bit, and they're like, well, there's no wind, and so, or there's no wind, there's no sand. And then we figured out, well, there are high concentrations of methane ice right here that got blown off some ice caps in the very rare and thin winds that do exist on Pluto. It can work. And so we think it's methane sand dunes on the surface of Pluto. So crazier and crazier as we go. Just to finish off, back to Titan again. We're so excited about Dragonfly. It's being built. We're going to go through a critical design review in the spring and then start building it. And we'll launch in 2027. We're having science team meetings all the time and getting ready to go there and getting ready to know what we're going to be looking at and looking for. And we can ask these big questions. What makes a planet or moon habitable? What chemical processes led to the development of life? And has life developed elsewhere in our solar system? If we see it there, there's no way it could have been brought there from Earth exchanged from Earth, like maybe with Mars, we could exchange life between Mars and Earth, but not way out there. It would have to have its own origin. And so, yeah, by mid-2030s, 2034 will arrive, and I will have my handful of sand on Titan. It can't bring it back to me, sadly, but I can look at it and be very happy about it. Thank you very much for listening.
Now, I can see very much, especially for us here, we're looking at means that we gain more knowledge, but someone's going to come along with dollar signs in their eyes. And so what prospects is there for commercialization of minerals or other things to mine?
Yes, so it turns out that there are a couple of asteroid mining companies, and they're in the black. So they have figured out a way to make money without actually going to mine yet on an asteroid. And I think they're selling some technologies and other things like that. I don't know what's happening, but
Speculators in there.
yeah, but I think the idea is, well, if you go to an asteroid, you don't need to go to where these elements are concentrated like we do on the Earth and dig way down deep and go, remove mountains. Instead, all of it's just sort of scattered in and among the rocks on the surface in kind of lowish but better concentrations than on Earth, where everything's sunk down to the core. And so you can go and mine a lot of precious minerals a little more easily on an asteroid. There was even an idea to go grab an asteroid and bring it close by. Like, how good of an idea is that? I don't know. Because we also just launched a probe to go and see if we can nudge an asteroid, right? In case one comes too close. Mm-hmm. So I don't know if people would be too excited if we bring one close on purpose. But that's a very real possibility. Or even mining on the moon. You have to deal with a little more gravity on the moon. It's so easy to just sort of, step off onto the asteroid and then just sort of step back off again. Not so on the moon. But somewhere like Titan is very rich in hydrocarbons. And there are just tons and tons, immense volumes of hydrocarbons. And so if someone could go and just sort of scoop some out of the oceans and bring it back, that's another idea, right? You could do the same, pick out, heavy helium that's in Saturn's atmosphere. I forget what we would be mining out of Saturn's atmosphere. But there are a number of things that we could think about. But do we really want to bring more hydrocarbons here? I mean, in some ways, yeah, we'll run out of it eventually, but let's hope that we don't burn it all and put it in the atmosphere first.
Have we already contaminated Mars?
Maybe locally, because as they returned, I think, to the Surveyor mission, Surveyor lander, and that was, which Apollo 14 went there, and I think they swabbed the spacecraft and found some living bacteria on it. They've been there for several years, 3 years.
That's
not necessarily on the moon. Yep. So, well, maybe. I think we've been trying to be more careful for Mars. We weren't careful at all for the moon, because why should we be? But I think from the beginning we've tried to be careful on Mars, and that costs $40 million extra every time we want to clean something. We're fairly good at it. I don't know.
So we have a lot of mechanical movement here. And how do you engineer for the cold and the wind and the sand?
The answer is I don't know. I know they are thinking very carefully about all of that. And there's even the potential for, there's lots of organics. Could it be sticky? Could it stick inside the rotor? Could it stick in the inlets? Could it, we're kind of counting on the fact that it should be a fairly dry desert based on all kinds of other information that we have about the landscape. So we're counting on that. And then we're getting better and better at cold technologies. In fact, it's called cold tech. You can apply for grants to do that. So all the different, lubricants and materials or whatever are very specifically designed for those temperatures.
In a former lifetime, I'm a Class A toolmaker machinist, and to answer your question, a couple of places where I was working, we were working on government contracts, and there's some very exotic metals that government actually invented and that we had to work with and machine, and some of them are good as far as very little expansion or contraction. And extreme temperatures. And so you can cut to close tolerances, you do not have to lubricate it.
And one other thing we'll do too is we'll use the waste heat from the nuclear battery, the power source that will charge up the battery, and that can actually keep the instruments warm in a certain area of the spacecraft. There's some areas we don't want to stay warm, we want to equilibrate with the atmosphere, so we can measure the atmosphere and find out about it. So there are some serious kind of firewalls in between things we want to keep warm and cold. Anything else?
What's the expected lifespan?
3 years. The mission duration, I think, is 90 days, but we've done that before with the Mars rovers, and that one lasted 14 years. So I think we kind of easily think we'll get to 3 years.
Is your selected spot on the equator?
Yes, it is. It's right at the equatorial regions. There's a sand dune and then a little impact crater right at the top of the sandy area. So we'll land just below that crater in the sand first, and then kind of make our way up onto that crater.
So we know how missions get delayed.
Yeah.
So are you subject to planetary alignment to get there, or season of Saturn?
Season to some degree, but I think we've got some leeway. So the seasons on Titan are each 7 years long. A year is 28 Earth years. And so we do have time to work with in terms of that. And already we've been through a delay, and actually that was a major rebudget. I don't think anyone's anxious to do that again. It was a year delay because of COVID, and that shoved the launch out. It shoved the early part of the mission out, and I think everyone was like, okay, we could just go. And I think the extra years at the beginning has kind of given everybody a good jump start. The mission is being designed and run out of Johns Hopkins University Applied Physics Laboratory. They're sort of I want to say it's like a startup mission company. I mean, they've been doing government contracting for a long time, but as far as space missions, they did the Mercury Messenger mission, they did the Pluto New Horizons mission, and they're doing, I think, Lucy that's going out to some asteroids. But otherwise, JPL is the powerhouse that just cranks them out and spends a huge amount of money. And so I think APL is trying to stay sleek and really focused on this mission. It's their flagship right now.
You're working towards a specific launch window?
Yes, there is a launch date. It's something 2027. So it's like we'll be there in very
You've got a deadline to see.
Yeah, exactly. And it's down to the day. Yeah. So.
Do you know are you doing like the slingshot stuff?
Yes, it's what is it? I know there's a Venus portion to it. It might be Venus, Earth gravity assist to go out. We won't get a Jupiter flyby, but it's going to be sitting here in its capsule anyway, and so.
Does APL have a clean room like JPL does that visitors can kind of watch what's going on?
Yeah, there is somewhat of one. They're pretty close. I have to know what they're doing, but yeah, that would be really cool. I'll ask and see if there's any way to for people to come and be tourists and see what's going on. I think that would be really cool.
Awesome.
Yeah. So far, they're not cutting metal yet. I mean, there are prototypes and portions of it that are designed. They're taking out the quadcopter with the sort of software in place, the bare bones of it in terms of navigation out to the fields. These quadcopters that Penn State is developing. So those tests are happening. Oh, and I think actually they took it out to the Algodones dunes that are in California. They did that just earlier this year. So it was pretty successful. All right. Oh yeah, one last.
Are we going to see any more on how the universe works?
Yeah, that's a really fun show to be part of. It's a Science Channel show. If any of you have seen it, How the Universe Works, they do a great job. They're really good at their research. It's a British film company, Pioneer Productions, and they've got a lot of people. In fact, sometimes they say, oh yeah, I think this and this, and I'm like, well, I think we just read this, and I go look, oh yeah, you're right. So they do good research. And in fact, out in the field, I heard about this Mars core just this summer, and had to kind of quickly put something together about that because one of them had heard about the results. So anyway, we did film this summer at Little Sahara down by Delta, and usually the episodes come out in like February through April or something, at that time period. I never know exactly when. But yeah, I love their show. I love that I get to be part of it. It's really fun. Okay, thank you all so much for coming. Thank you.